Namaskaram. Today we will discuss about vector field and its properties. Actually, this is our last homework, and there is a correction in this third problem. This point is not 4, 5. Actually, this point is 4 minus 5. Then only you can evaluate the directional derivative. Okay. Okay. Anyway, these are the solutions of last homework. Okay, let's start our new session. So this is the formal definition of vector field, and it's a very simple definition. A vector field in a plane, first of all, we consider a two-dimensional plane, is a function that associates with each point P in the plane a unique vector of P parallel to the plane. Okay, that is Fp equal to Fp is a function, it's a vector valued function. Okay, and what is vector field? We assign a vector at each point using a function. Okay, for example, you consider a plane like this. Suppose this is our point P. Then we have a function. Suppose our function is maybe like the f of xy equal to xi plus yj. Then what we'll do? First we identify the point. Suppose this point is 1, 1. Then we find the function. Sorry, this is suppose this function is find the function f of 1, 1. What is f of 1, 1? This is 1i plus 1j. That is I plus j. Then you identify this vector. What is I plus j? I plus j is a vector like this. So suppose this point is 1 second. Okay, anyway, okay. So what is this vector I plus j? I plus j is a unit vector like this. Then we shift this vector at this point. Okay, then we shift this point at this point. That's the idea. So we assign a vector at each point of a plane is called vector field. Similarly, we can define the vector field in three-dimensional space. We assign a vector at each point in three-dimensional space using a function. Okay, that is called a vector field. There are several examples. First one is a gravitational field. What is gravitational field? These vectors are the gravity. Okay, gravity experience at that particular point. Okay, so we know that so this vector represents the magnitude and direction of the gravity. The direction of gravity always towards earth, and its magnitude depends the distance from the origin. Origin means distance from the earth. Okay, so if distance is high, then its magnitude is less. So that's why a vector field like this is actually three-dimensional vector field. Okay, not only 2D, it's actually 3D. Okay, this is also another vector field which contains velocity. This is a fluid flow. Suppose this is a fluid flow. Then we can assign velocity vector at each point. That means this vector represents velocity at this point. Okay, this vector represents velocity at this point. Okay, similarly, we get a velocity vector. It is a fluid flow. Okay, for example, consider a vector field. Sketch the vector field fxy is equal to yi minus xj. Then how to sketch this vector? The two dimension. So draw this. And first of all, we have to identify point. Suppose we consider the point 1, 1. So this is the point. Suppose this is our point 1, 1. So we have to assign a vector at this point. Okay. So to find that point, first of all, we have to identify f of 1, 1. What is f of 1, 1? Again, I minus j. So first you identify the vector I minus j, then plot that vector at this point. That's the idea. So what is I minus j? I minus j means in x-axis its value is I, and its y-axis it is minus 1. So the point is somewhere here, and this is the vector. Actually this is the vector I minus j. Okay. So for a vector field, we have to plot this vector at this point because we have to compute this vector at the point 1, 1. Okay, so in a vector field we have to plot this this vector at this point. So we get like this. Okay, you got the idea. So we have no need to draw this vector. We have to assign the vector at that point. Similarly, you consider another point. For example, you consider some point. It is called suppose it is 0, 2. This point is actually 0, 2. Then what is f of 0, 2? F of y value is x value is 0, so there is no j term. So this is 2y. And what about the vector 2y? We know that vector 2y is like this. Suppose this is our 2. Then vector 2y is this vector. Okay. Then you shift the vector at this point. So we get a vector like this. Okay, you got the idea. So we get a vector like this. So similarly, we can assign vectors on every point. For example, you consider a point here. Suppose this is actually this point is minus 1, 0. What is the vector at minus 1, 0? First of all, we have to calculate f of minus 1, 0. X value is minus 1, so this term is j. And y value 0, there is no I term. So actually f of minus 1, 0 is j. And what is j? J is a unit vector in y direction, isn't it? So actually j means a unit vector in this direction, like this. So you shift the vector at this point. So we get like this. So after plotting all the vectors in this space, we get a vector field. Okay. So I think now you understand how this vector field behaves. So I will show you the exact figure. So this is the shape of the vector field fxy equal to yi minus xj. Okay, if you plot so many vectors, then we get like this. So vector field is nothing. We have to assign a vector at that particular point. That's all. We choose a point, then assign the vector at that point. We choose another point, we assign the vector at that point. That's all. Okay. Normally, vectors are always starting from origin. But in the case of vector space, we identify the vector, then shift the point. Shift at that point. Okay, that's the idea. Another standard vector field is gradient field. It is very easy. The vector field defined by gradient of a function f is called gradient field of f. Okay. Suppose we have a function, a given function fxy is a two-dimensional function. Then you simply evaluate the gradient of this function. It is a vector valued function. Then you then you identify the vector field corresponding to gradient. Okay, because gradient is a vector valued function. So we know how to compute the gradient. Gradient is defined by like this fxi plus fij plus fzk. This is for three-dimensional case. If it is two-dimensional, then there is no last term. It is only fxi plus fij. Okay. Then we compute the gradient, then plot the gradient in a given space. If it is two-dimensional space, then yes, first of all you identify a point, then compute the gradient at this point, then plot the vector at this point, then you take another point, compute the gradient at this point, then plot the vector at this point, like this. Okay. Then there is a natural question: what is the meaning of this gradient field in a space? We know gradient has a very important property. It always gives the maximum rate of change direction. Okay. So the vector at each point in a gradient field gives the direction in which rate of increase of f is maximum. Okay, that's the idea. You choose a point, suppose here the vector is like this, and what is the meaning? At this point, this function has maximum rate of change in this direction, and this magnitude of this vector gives the maximum rate of change. So that is the advantage of gradient vector field. Okay, this is another definition related to vector field. Like a vector field f in 2D or 3D, 2D space or 3D space is said to be conservative if it is the gradient field for some function phi. Okay, so a vector field is conservative if it is gradient of some function phi. Okay, phi is a real valued function. That's all. So this is the idea. That means f is of the form del phi for some phi. Okay, so a vector field f is conservative if there exists a function phi such that f equal to del phi. Okay, if it is possible, then this phi has a name that is called potential function for the given function f. Okay, f is given. This vector valued function is given. If it is exist a phi such that del phi equal to f, then f is called conservative and the function phi is called potential function. Okay. Okay, problem. Show that phi equal to x square minus 3y square plus 4z is a potential function for 2xi minus 6yj plus 4k. So it is very easy because f is a potential function of phi only when del phi equal to f. So you simply evaluate del phi. How to find del phi? Del phi is nothing, it is phi xi plus phi y j, because it's a three variable function, and plus phi is a k. Okay, what is phi x? To differentiate this with respect to x, then we get 2xi plus what about phi y? That is minus 6y. Okay, so this is actually minus 6y j, and last one is phi z, derivative of phi with respect to z, that is 4. So plus 4k. So this is exactly our f. This is exactly our capital F. So what happened? So del phi equal to f for this function. Okay. So f satisfies this condition. So f is a conservative. This f is a conservative vector field, and phi is the potential function for phi. This phi is not unique. Suppose if you add some constant, suppose it is some 10 is there, no problem, because derivative, after if you take the derivative, there is no effect of this 10. Okay, so again this function also, this new function, this plus 10 is also a potential function. Okay, so in general, potential function is not unique if it is exist. Next problem. Find a potential function for f. F is equal to cos y plus y cos x I plus sin x minus x sin y j. Okay, so how to find the potential function? We know that the potential function satisfies the relation f is equal to del phi, where phi is the potential function. Okay, that is, this is equal to phi x I plus phi y j, because this is a two variable function, x and y alone. So what is f? F is given. F is equal to cos x plus y cos x I, and like this. So we can compare the I part and j part. So comparing I part and j part, we get phi x and phi y. What is phi x? Phi x is given by cos y plus y cos x, and phi y is equal to sin x minus x sin y. Okay, so we have to find phi. So to find y, we integrate these two functions. First you integrate this function with respect to x, and next we integrate this function with respect to y. Okay, so if you integrate this equation with respect to x, what happened? LHS become phi. Phi is equal to uh, x cos y plus y sin x plus a constant of integration. But here we integrate with respect to x, so our constant of integration is a function of y. Okay, and similarly next we integrate this equation with respect to y, so LHS become phi. Phi is equal to, what is the integral of this function? This is y sin x, because we integrate with respect to y. So this is y sin x plus x cos y plus a constant of integration. In this case, the constant of integration is function of x. Okay, you take another function, it's f2 of x. They are arbitrary functions. So both are phi. So by comparing these two phi, because these two functions are same. So comparing these two functions, what happened? We get, if you equating these two, because LHS are same, so you can equate the RHS and cancel these two terms. We get f1 of y is equal to f2 of x. That means a function of y is equal to function of x. That is possible only when it must be a constant. Okay, otherwise they are not equal. So a function of y equal to function of x for all x and y, that is possible only when it is a constant. That means the conclusion, this function is constant. So what is our phi? So phi is nothing, x cos y plus y sin x plus a constant. You can choose any arbitrary number here. So it is clear that this phi is the potential function for this vector valued function f, because this phi satisfies this relation, and this phi is a potential function. Okay, if you choose c equal to 0, then we get a simple potential function. You can choose any c, no problem. Okay, so this is x cos y plus y sin x plus c. This is a definition of divergence. If f is a vector valued function like this, f of fxy is a real valued function. Fx y z I g of j h of k, then the divergence of f is defined by dou f by dou x plus dou g by dou y plus dou h by dou z, and it is denoted by div f. Okay, so corresponding to vector valued function, we can define, actually this is a real valued function, there is no ijk terms. Okay, so this is div f, and if you denote the operator, if you define an operator like this, it is called our del operator. Okay, dou by dou xi, dou by dou yj, dou by dou zk is an operator like a function. Okay, then we can rewrite this divergence of f using this notation, isn't it? You think about this operator dot our f. What is our f? Fi plus gj plus hk. Then what is our dot product? Dou by dou x of f plus dou by dou y of g plus dou by dou z of k. That is exactly our divergence. Okay, so we can define the divergence in terms of this del operator. So this is a compact notation. Div f is equal to divergence of a vector field f is equal to del dot f. Using this del operator, we can also rewrite or denote our gradient using del f. Okay, because gradient is nothing. Suppose we have a function. Suppose we have a function f, then we can find the gradient using del f. Oh, sorry. In the case of gradient, this is not a vector function. It may be a like a normal function, not a vector function. Then we can write the gradient as del phi, not a vector function, because gradient, we evaluate the gradient for real valued functions, not vector valued functions. So here only difference is f is not a, it's a typo. F is not a vector valued function. It's a normal function. Then we can denote our gradient by del phi. Okay. Okay, next next definition is curl. Curl of a function, vector function. If f is a vector function like this, then the curl of f is defined by it's a determinant of, actually it is a del cross f, the cross product of two vectors, because del operator is also a like a vector and f is a vector, so you can think about its cross product. So this is actual definition I j k, and this is dou by dou x, dou by dou y, dou by dou z, and FGH are the components of given function. If we expand this determinant, we get the curl of a vector, given vector function. Okay, a very simple definition. We can view this as del cross. It's like our cross product of two vectors. Actually, del is not a vector; it's an operator. But you can think about it as an cross product of two vectors. Okay, next problem. Find the divergence and curl of the vector field fxyz is equal to x square yi plus 2 y cube zj plus 3 zk. So first you write the formulas of divergence and curl, then you compute the compute that divergence and curls this function. These are the formulas for evaluating divergence and curl. So first we have to evaluate the divergence. So okay, it is clear that the component functions are, this is our f and this is our g and this is our h. Here f is x square y, g is 2y cube z and h is 3z. So you simply evaluate these derivatives. So what about dou f by dou x? It is 2xy plus, next one is derivative of g with respect to y. It is nothing, 6y square z. 6y square z, and plus the derivative of h with respect to z, that is 3. So this is our divergence. Okay, so divergence is 2xy plus 6y square z plus 3. So next we have to compute curl of this function, and this is the formula of curl. So this is equal to Okay, so here f is x square y and g is 2y cube z and h is 3z. Then if you expand this determinant, we get like this: f is equal to dou by of 3z minus dou z of 2y cube z times I plus dou z of x square y minus dou x of 3z of j plus dou x of 2y cube z minus dou y of x square y of k. Okay, upon simplification, we get this is equal to minus 2y cube I minus x square k. So this is the curl of this function. So curl of is equal to minus 2y cube I minus x square. Okay, so this is a very simple process to evaluate divergence curl of a function if it is given. So this is your homework. All of you submit this homework through using your Google Classroom. I will post this homework as an assignment in your Google Classroom. Okay, thank you.